So I'm not gonna use I'm not gonna use the webcam if that's okay for you, because anyway, I hope you focus on the slide rather than on me and my cats. They're around, but maybe later for the question I can switch on the webcam. All right. So what I'm going to talk about is a general introduction on, so like a magic of, as you see the title, the magic of nuclear. I'm going to give you a lecture on nuclear physics. There are way more advanced people than me in doing so. I wanted to show you how we can apply nuclear physics in a specific field, which is particle therapy. So I'm going to give you a few introduction about particle therapy, and then I'm going to show you an application. Okay, what is particle therapy? In general, what is radiotherapy? Radiotherapy is, the goal is to use radiation, is the use of radiation for killing tumor cells, and at the same time minimizing the damage to the healthy tissue, so to avoid or minimize possible side effects. Radiation therapy, which is radiotherapy, radiation therapy, you will find it under many names, has become in the past decades a very like one of the pillars of the cure against cancer or the treatment for cancer. You know, the let's say the other one are chemotherapy. Well, actually, I would say four, because there are chemotherapy, immunotherapy, which is a mix of both, which is has become very popular more recently, and of course surgery. Usually, cancer patients do not undergo only a specific one type of treatment, but so only surgery or chemotherapy, but a mix of maybe more than one. And therefore, we call it radiotherapy is a multidisciplinary approach to cancer care. And about 50-60% of our cancer patients today, they undergo radiotherapy as part of the treatment. Sometimes is for a cure, is used as a cure, other time is a palliation. Is mostly used for is not used for every type of tumors, but it depends on, of course, on the tumor time. And so for some tumors is very effective, for other is not used at all. The number of, as I was saying, the number of cancer patients that actually undergo radiotherapy has increased incredibly. The first patient, keep in mind that the first patient were treated, they started to treat and to explore this tool in the, let's say, maybe in the between the 50s and the 70s, but let's say the use has been growing exponentially in the past, maybe I would say 30 years. What kind of radiation? Up to now, I just told you radiotherapy, using radiation to kill cancer cells. But what kind of radiation? In the past 70 years of this exploring this field, people have been testing different type of radiation. Some neutrals, like neutrons or X-rays or photons, and others are charged particle. And you see in this, let's say in this chart here, these are all the different particles that have been tested. So some are like the usual suspect, and some of them are like maybe more exotic, like pions. People have been using antiprotons even, which are not in this chart, and even very heavy particles. So from protons up to argon. Argon is so far was the heaviest particle used. The most, and each of these particles had some biological or physical aspect which were interesting and possibly appealing for this application. However, right now the most widely used are X-rays. In any big hospital, you do have at least one. Now every big hospital is equipped with at least one Linac or more. And so most of the cancer patients, they undergo radiotherapy with X-rays. However, in the past, let's say 20 years, maybe 20, 30 years, the application of charged particle is gaining a lot of popularity. Currently, the charged particles that are used for treating patients are protons and carbon ions. And this is just to give you an idea how the number of, this is I think from last year, or it's a very recent the very recent chart where you see how the number of patients treated in the different countries for with protons or with ions. And you see the number is quite, I mean, it's not as, I don't have the number for X-rays, of course it's going to be much higher, but just to give you an idea that the spreading of these facilities around the world. Or you can see like this is a number of facilities which has been growing really exponentially. And in Italy, for example, we do have 3 facilities, Trento, the one in Trento with protons, the one in CNAO, the one in Pavia, CNAO, which is heavy ion centered, where they can deliver both protons and carbon ions, and the one in Catania at LNS, National Laboratorio Nazionale del Sud, where they treat with a specific tumor, the eye tumor with protons. So a few words. First, I want to kind of convince you that, you know, ions do have a certain number of benefits against photons. Before I say, I mean, I start into that, before I go deep into this topic, I just want to, the message I want to convey, there is no magic particles. Whatever radiation you think, there is no radiation that is the best. Each radiation, I mean, the type of radiation is, each radiation would have pros and cons. And the way I see it, even if, you know, I'm an ion person more than a photon, but the idea is that all this should be tools that should be used based on the patient situation, okay? So that there are definitely a number of, the physics tells us that, at least the physics, biology is a whole other matter, but the physics tells us that ions are superior to photons for certain aspects. So here you see, and this is the reason why, I mean, this is let's say the advantage of ions are, the benefits of ions are in the physics. I mean, also in the biology, but mostly in the physics. Here you see the dose deposit, or the energy released by radiation, by the radiation, versus as on the Y, and on the X you see the thickness of our target, so the patient, okay, how deep the radiation penetrates. Now, when I say, maybe I should say this, it's trivial, but maybe it's not, that when we say the radiation kills, I mean, the radiation is used to kill cancer cells, it means that the radiation deposit energy, which kills the cells. Okay, so that's why we're going to look at the energy deposition of radiation. Now, if you look at how X-rays, they lose their energy, they have a peak and then a decrease. While for all charged particles, so you see here protons and ions, but this is true for all charged particles, you will see they deposit very little energy up to a certain point where they deposit most of the energy, and then they are, which is their, and then the energy position go to zero. This position, or the maximum energy position, is the place where is the depth at which the particles stop, so they lose most of their energy, and their kinetic energy in the stuff, and this is called Bragg peak. Now you already start to see, let's say that this is your tumor. If your tumor is seated at a certain depth, that you can deposit, you will deposit with ions most of the energy in the tumor, while very little energy in the healthy tissue. You can't really do that with X-rays. Now, the position of both this peak and this peak depends on the particle energy. So you can move it by changing the energy, the position, not of the tumor, but the position of your maximum energy position will increase or decrease depending on the energy. This is true also for X-rays, but you will never see X-rays that deep. The peak is always going to be much more superficial. So you can see here that definitely you can start to understand that maybe ions are better than, could be superior than photons in sparing the healthy tissue. Oops. Okay. So if we see now let's say in the tumor, more in an actual picture, that's a CT scan of a patient, and you have the beam, and then you see where your tumor. Ideally, what you would like to give is all the dose in the tumor and zero dose elsewhere, because you want to avoid unnecessary exposure of the healthy tissue. However, this is not possible because the radiation has to penetrate and actually reach the tumor. But therefore, but anyway, you do see that the let's say the dose deposited by ions is much lower than photons if we're treating fairly the tumor. Of course, if the tumor is here, the difference is a lot less. So again, keep in mind, there is no magic particle, depends on the situation. If you're looking at the, now this is, again, so I show you first the physics. You knew, with the people who study actually this energy position, they knew nothing about radiotherapy, and they didn't know that by studying this interaction radiation with matter, they actually would end up treating cancer. But then people, of course, then I show you something more on the let's say the application of the tumor. And now I'm showing not like this is a treatment for so like the dose deposition on an actual CT scan of a patient. This is I believe it's a 10-year-old kid, who has a medulloblastoma, which is a brain tumor, very typical for a pediatric patient. And you see, this is a dose deposited by protons and photons. The irradiation area, this is a spinal irradiation, where you do irradiate from the top of the head and all this. Okay, you're irradiating the whole spine, and you would like to see red here and gray elsewhere, because elsewhere is healthy tissue, and you do see that protons in this case are superior than photons in sparing the healthy tissue. Okay, so I hope that with this, at least I show you for certain aspect how charged particles are superior to photons in certain cases. Before actually going to the actual magic, the magic trick, I want to say a few more words on like some aspect of radiotherapy, because right now I talked to you about physics and about the nice energy deposition, the peak, the Burke curve. But maybe you're still asleep, maybe you don't, but maybe you thought, okay, the peak that I show you is maybe a few millimeters, the width is a few millimeters. How am I going to cover a tumor? So if you can, let's say so I wanted to show you how you can go from that for the pure physics to the clinical application. The challenge is a single beam, a monoenergetic beam. You can irradiate a region whose size, imagine it's approximately a cent, the coin, 1 cent coin. And instead, your tumor is like a golf ball. Tumor size varies. It's very, the range of tumor size is very broad. They can be super small, they can be pretty big. But let's say on average, they are in the order of 1 cubic centimeter. So what you want to do, if you want to irradiate this with, you want to cover your ball with we gotta transform our 1 cent coin into a golf ball. So how do we do that? Let's start with the depth. So let's say let's consider the tumor like in let's say two different sizes. We have the section, like the aerial section, which is what, if we're the beam and we're looking at the patient, that's the area of our tumor. And then we have the depth. So from the surface of the patient, how deep the tumor goes. So let's start actually with the depth. With the depth, I already said it before, not specifically and not explicitly, but I did say that the position of the Bragg peak change. The Bragg peak is where we want to have our tumor, or the other way around. We want to position our Bragg peak at the depth of our tumor. Now, our Bragg peak is a couple of millimeters, and our tumor is about 1 centimeter. So what do? We change the energy, and the position of this depends on the eye energy. So we do change the energy to cover the entire tumor region. So the lower is the energy, the earlier the Bragg peak will appear, because the earlier the particle will stop, the less patient it will traverse. As we increase the energy, this peak is going to move. So if we use several monoenergetic beam, we're going to cover the whole tumor depth. So we go from what is called the single Bragg peak to a sum of Bragg peak, or called SOBP, spread out Bragg peak, which is going to cover an entire, like the tumor length. There's still another thing that we gotta keep, that we gotta use, and that is the aerial. We gotta cover now that we did cover. You can consider like cutting the tumor in slices, and each slice is a tumor, is a single Bragg peak. So with the spread out Bragg peak, we cover the whole tumor, but we still need to cover the area of the tumor. So let's say now here is more putting together the let's say all the pieces, where we are in our facility. So we produce our ion, which could be a proton and a carbon. We need to accelerate the ions in cyclotron, if you're talking about protons, or synchrotron for a heavier particle like carbon, to reach the desired energy. As you mentioned here, I waited here to mention you that the energy we are considering to have the actual range to pass the human body and to reach the tumor depth is about 200 MeV, up to 200 MeV for protons, and up to 400 MeV per nucleon for carbon, 450. So that's why you need cyclotron or synchrotron. Once the energy is reached, you have a single spot, like a small beam, and you use magnets. And let me show you with this movie, which is much better than any way I can describe it to you. You see now that pencil, that small beam, is the single monoenergetic beam of a single energy, which is moved to paint the tumor surface with magnets, with dipoles and quadrupoles, which covers then the entire tumor area. So you choose an energy, you scan, you paint your tumor, then you change the energy, and you go to the next slide. And so like this, you go from a 1D ion to a 3D volume. And this is done by controlling the beam and controlling how much dose each spot is going to have. It's what the treatment planning system does. Now, so let's go to I don't know how many minutes I still have. Hopefully maybe 10. I hope so. I'm going to show you where fragmentation, or where nuclear processes occur, and how we can use them as in our favor. As you probably imagine, the number of physical processes that occur when radiation interacts with our body, or when they in radiotherapy, is many. So for sure, energy loss is the core, what actually makes it possible for radiation to kill tumor cells. So we do want energy loss, which is an electromagnetic type of interaction. You have another important process, which is Coulomb scattering, which is also electromagnetic. And then you have the nuclear fragmentation. Nuclear fragmentation, as well as the others, they occur every time radiation passes some material, so including our body, and is going to influence the dose delivered by radiation. What I wanted to focus, or I want to tell you, is probably electromagnetic, and the Coulomb scattering, but maybe not everybody is familiar with nuclear fragmentation. Nuclear fragmentation is a strong type of interaction where your projectile, so like your ion beam, will hit the target, so the nuclei of the projectile and the target. So in our case, the beam, the proton and carbon, and like our body. they will overlap, and the overlapping region will be scraped away, creating a number of fragments, whether they are single nucleons, so protons and neutrons, or they are heavier nuclei. They are after the first stage of interaction. The targets and the projectile are in an excited state, and they will decay, emitting photons or nucleons or heavier ions. So long story short, what nuclear fragmentation does is creating fragments, so particles of different energy and different charge than the primaries. So these fragments, they can deliver a different dose, because the dose is the dose deposited by radiation depends on the particle charge and particle velocities. So you create different particle, you do give a different dose. Different dose means different biological effects. So the effect, I'm not going to deal this, but the effect of nuclear fragmentation is basically, now let's say this is a very dense slide. I'm just want to give you a general idea. So this is treatment planning for a head and neck tumor with carbon and with protons, which are the two ions used right now. And also in the middle, you have helium, which is a candidate ion today, a very promising candidate ion to be added together with protons and carbon. Now, the effect of nuclear fragmentation, what it does is that instead of just seeing a red, this is where the tumor is. So ideally, you would like give the dose here and nothing else around. But what you do see is actually a dose in the close in the surrounding, in the, let's say, the entrance channel or in the tail, the side of the tumor. And you do see that this region here and here and here, there are different colors. The fact there are different colors is due to the fact that there is a difference, that there is a different fragmentation processes and different fragmentation products when carbon ions will interact with matter compared to helium, compared to protons. Carbon has 12 nucleons, helium has only 4, hydrogen cannot really fragment, is only going to fragment the target. So therefore, nuclear fragmentation does have an effect, which has to be taken into account in the treatment planning. Before I get into the actually how we can use it in our favor, I just want to tell you what are some challenges in ion therapy. And the reason I want to say that because one of the challenges that we are going to approach, or we're going to address. There are many challenges in ion therapy, as you might imagine. Some of them are pure physics. Some of them are more biological or clinical. One of the most important one is actually the verification that what we are shooting is correct in terms of the dose that we're giving to the tumor and the position. Are we really shooting the tumor, or are we shooting also the healthy tissue around it? Are we misaligning our patient? So one of the major challenges has been an online tracking of the beam, on online monitoring of the beam while irradiating your treatment planning. And this is what, I mean, I leave here the other challenges, but I want to go directly cut to chase and to actually go directly into this challenge. So how can we exploit nuclear fragmentation to actually obtain an online monitoring of the peak? Sorry, just a second. Okay, 5 minutes more. Yes, I'm almost done. So as I said before, the nuclear fragmentation, so the fact that the ion beam is going to interact and fragment inside our body, creates a number of particles, tons of particles, which could be neutral, so it could be neutrons, it could be photons, or it could be charged particles, which are emitted at different angles and energy. So imagine like this is your beam, this is your tumor, and you have a swarm, like a cascade of particles going everywhere outside from the patient. The interaction probability increases with that. So you will have the highest number of particles produced at the tumor site, where the ion beam is at the lowest energy. So around the Bragg peak, so where the tumor is. This idea, the fact that fragmentation occurs, the highest fragmentation occurs in the tumor, has been exploited actually by, let's say, some smart physicists to say, okay, but if we do see that the highest production is at the tumor, the highest production of particle is at the tumor, then by detecting this particle, we can track back and find out where the tumor is. So this is the base of which, for example, the proton emission, positron emission tomography, the PET, not the diagnostic PET, is the other PET, is another PET is based on. Or I don't know if you heard, if you ever heard application like this. So people have been looking at the prompt gamma emitted from the tumor or the charged particle emitted from the tumor, track them back and point, say, where the tumor is. Now, each method has pros and cons. Sometimes there is a very limited spatial resolution because you can't really track back because of the multiple scattering of charged particle. You're limited. You can't really track back to the exact point. Sorry, just a second. Okay. Should I answer the question now, or should I wait till the end? Roberto? You want me to answer the question now, or do you...
No. Please go ahead. Just.
Oh, okay. I'll keep the question here. Okay. So, so as I was saying, each of this method has a limitation. They have pros and cons. Now, the one thing that I should say is that each of this method rely on the fact that the particles are produced by the interaction of the radiation, the incoming radiation, with our body, especially in the tumor. We thought about doing a different approach. So we still want to exploit the fragmentation, so the nuclear interaction of the beam with the patient and with the tumor. But what if we could actually enhance the production of particles, in our case, prompt gammas, by loading the tumor with a specific element, which is going to give us a signature spectrum, so specific gamma that you can only see in the tumor. So we want to find a magic element. The magic element in our perfect world would have the production of very high energetic gammas, which will increase the detection probability. We'll have a signature of specific gamma, which are like some specific gamma that we can detect. They're only going to be produced in the tumor loaded with this element. It should be no toxic. It should have high selectivity. So we looked at several elements, and the magic element we found is actually 3 possible candidates. One is fluorine. So the idea, fluorine, why fluorine? Because fluorine is already used in diagnostic, and it has a carrier. You keep in mind that we want to load the tumor, and to load the tumor selectively, so only the tumor and not the healthy tissue. We gotta find something that targets the tumor. So in our case, the carrier of the tumor is the FDG, which is already used in diagnostic. Fluorine as a plus that produces high energy gamma of about 6-7 MeV. The other 2 candidates, they come more from this copper is from diagnostic, and yttrium, which I didn't know before actually I started looking into elements. I didn't know I didn't really I never know the existence of yttrium before. These are used for, this is a tool for diagnostic, and instead yttrium is used as a for radiotherapy, local radiotherapy. So like element for radiotherapy, like for example iodine, so like for thyroid tumors, the same concept. Both of this, they already have carriers that are non-toxic. They're already used on humans, and they also produce high energy prompt gammas. This energy, I should say that the high energy prompt gammas, they mostly come either from the excitation after fragmentation, or the excitation, nuclear the excitation of the element, the copper or the yttrium. So a few more slides and I'm done. We did not do any experiment yet. We just started with Monte Carlo simulation, where what we wanted to see is if we load our tumor, if we have a tumor completely made of tissue or made of, instead of this element, are we going to see a difference if we shoot this tumor with a proton beam, and are we going to see a difference in the prompt gammas? So we did our simulation, and that's what we found. This is our background. This is the prompt gamma they're going to be emitted if the tumor is not loaded with anything. So you do see, you do see three signature peaks, which are the carbon and oxygen, the excitation. We are mostly made of oxygen and carbon. We know that. What if we add to our tumor fluorine? Well, fluorine, unfortunately, does not really enhance. You don't really see, you do see an enhancement. So the black line is higher than the blue line, but you do not really see any extra peak, especially in the high energy region. The situation gets better if you have a copper or yttrium as well. Now, you do see some weird plateaus, and this is probably because JN4 does not have all the libraries for this prompt gammas. So to conclude, in summary, I hope that with my long introduction, I convinced you that charged particles are a powerful tool against cancer treatment, and the nuclear processes are an important aspect, and specifically nuclear fragmentation is an important aspect of charged particle therapy because it strongly influences the radiation biological effect. However, it's something that can be exploited, and in particular, like a brief idea that I gave to you and that we are considering is to use an element to load the tumor and exploit fragmentation and nuclear interaction to actually monitor, to look at the production of this prompt gammas and to monitor the position of the Bragg peak while we deliver the treatment. With this, that's the group at TIFPA, and plus people from, of course, the university, Cibio, FBK, and then other universities in Italy, other institutes around the world. I couldn't mention them all. And with that, I'm done. Thank you for your attention, and if there are questions.